Did it work? Did I typed start, but it didn't. I feel like it didn't show up in the chat.
Yeah, it did. It's all good. It's all good.
Oh, it did. Oh, okay. It didn't show up in my chat. Sorry about that. Hi everybody. This is kind of the final continuation of Chapter 7 for our introduction to statistical learning with Python, and then we're going to do mostly Chapter 8, which is about tree-based methods and models. So I'll just finish off Chapter 7. This last piece of Chapter 7 is about generalized additive models. And so the main import of these generalized additive models is we could take what we were doing in the rest of the chapter with like a single feature and extend it to like the multi-feature case. So this is the equivalent of moving from OLS to like multivariate OLS. So it's almost, I think, always that you would be using a generalized additive model and not a single feature model. So they're, I guess, important to understand. But yeah, I mean, there's not much to them beyond what we kind of already have covered. So basically just adding multiple, at least in the case of like models that can be represented with basis functions. So these kind of models that are just series of functions and covariates added together. You could follow the same strategy with a generalized additive model. You just keep adding functions and covariates, but the covariates change. So here's a kind of succinct mathematical representation of it. I guess I've botched that second J subscript there, but I'll fix that later. But yeah, and so you can see you're basically adding together each function as applied to a covariate for the observation I. So like to give you a better or like maybe a more concrete example, this is the example that the book kind of sticks with, is if you wanted to model wage or annual wage or whatever the variable is, you as a generalized additive model, and you have three features: year, age, and education. You basically just choose a basis function model for each of those and then stick them all together. So you can see in this case, they've chosen to model year as I think a natural spline. Yeah, oh, I see it. I have it in the caption. A natural spline with 4 degrees of freedom. Age is a natural spline with 5 degrees of freedom. And then education, which is a categorical variable, is a step function. And so then, yeah, you just kind of smoosh them all together and like literally. So like, and if you look at the model matrices, and I tried to make it pretty, but it didn't really work. But so this is the model matrix for the overall GAM, and you can see like the first, I guess they did first 4 terms are the terms for the natural spline that corresponds to a year, and then the 5 degree of freedom natural spline that corresponds to age, I think. Or did I reverse that? Yeah, age. And then the last one is the step function that corresponds to education. So they're just like literally, and so then you just do a regression, using this, and you can see like this last line here in the Python code is just like the regular OLS function fit on this. And then these get broken out, as dummy variables, I guess, these categorical responses. And yeah, so GAMs can also be used for classification in this kind of same, just because they are just linear models. We just kind of stick them in to the linear function part of the classification model. So here we have a logarithmic function or logarithmic regression, logistic regression, excuse me. And the kind of easiest way to represent this is you can set the log odds equal to the linear function, which in this case can be, the GAM. These are just the results from that modeling process. So I think I think they must have changed it. Oh yeah, yeah. So here they chose to do year using a linear function, age using a smoothing spline, and education again using a step function. So yeah, not too, they're really just linear models, I think is kind of the big takeaway. The only kind of wrinkle is with smoothing splines, which we know from last time can't be represented in this basis function kind of style. They have this parameter lambda, which is a shrinkage parameter. So that ends up kind of like shrinking the values towards like a maybe kind of towards the mean. You end up, instead of like maybe more extreme wiggles, you get fewer and less pronounced wiggles. So not quite towards the mean, but just kind of controlling the intensity and frequency of the wiggles, I guess. So that's difficult to do to represent, like, in this kind of simple model matrix format because there's kind of an algorithmic component to it. But you can use this package called Pygam, which is a pretty handy package. It seems like if you want to work with GAMs. So Pygam, when it comes to smoothing splines, uses an algorithm, which I spelled wrong there, called backfitting. And I think we've seen backfitting come up previously, but so basically the idea is that you hold all but one of the predictors constant. You fit you fit a model for that predictor, and then oh, sorry, I have some kind of alarm going off. I'm not sure what that is. And then basically like iteratively update by holding each one fixed in turn. And apparently it has some efficiencies because you can fit on the partial residuals of the model in each of those like iterations instead of having to recalculate the whole thing. So that's kind of a back of the envelope version of backfitting, but so Pygam implements that to do smoothing splines. And so it's really pretty easy to do. And in fact, if you just want to do a smoothing spline, you don't want to do a whole GAM, you can do that with Pygam because it turns out a smoothing spline is just a special case of a GAM. And so here's some code to do that with the shrinkage parameter set to 0.6, which is the kind of the default that Pygam implements. I don't know if everyone else knows this, but Reshape has this feature where if you use a -1, it imputes the number of rows from the number of columns that you assign in the second. So that's a little Python tidbit. If you don't just want to sort of like pick a lambda when you're fitting a smoothing spline, you can also use Pygam to sort of do a grid search to find the optimal lambda. So yeah, again, that's like pretty handy. So and I mean, if you look, it's like super easy. So here's some code for that. Yeah, and yeah, I mean, you can see the graph. It like these are, I think, like several attempts that it made, and then this brown line is sort of the optimal value, or the fitted model using the optimal value of lambda, which in this case was like pretty close to 0. I think I tacked those on, but I don't know that we need to look at those. I just, I think this is when I was worried we'd have too much time, so I added this little chapter question. So yeah, that's all I have on GAMs. I would, this lab, the whole lab is maybe not that good, but the part on GAMs I think is like educational. So if you did want to look at the labs and wanted to learn more about GAMs, I think I would recommend that. It's like the last third of the lab could be good to go through. But yeah, that's all I have. So. Oh no, I'll stop sharing.
Okay, nice. Is there any discussion? Does anybody want to bring anything back up?
I mean, one question I have is why you would ever choose a GAM over a tree-based method. If you're, want a more flexible fit, it seems like maybe the tree-based method is going to pretty much always beat the GAM in terms of flexibility. So why would you? And maybe it's easier to interpret, but I don't think they're that easy to interpret. So like, I don't know. I had some question about like why, like, what's the point of these a little bit, but other than that,
Good
no.
guess. Well, you go, Tom.
I was going to say I'd agree with that interpretability point. And you can use your knowledge of the domain to be like, I expect that these things are related linearly or in this way, and use the knowledge about each covariate to try and inform the model, and then you get interpretability as well. Whereas tree-based feels a bit more, not brute force, but a bit more less using your domain knowledge. If it was black box, I think you'd go for a tree method. Sorry, go on, Jack.
No, I was going to say I can make some guesses, like based on not based on nothing, but I wouldn't want to take the wind too much out of the sails of my own forthcoming tree chapter. But there are maybe a couple of lines towards like in the start, the high level things that don't necessarily answer it, but they hint to like why you might. But I do also think there's been a lot of advances in tree-based methods in, say, like the past 4 or 5 years. And with the added computation that we've got now, expensive like tree-based methods with additional like features added in, like XGBoost, like I think it would be quite rare that people would opt for like the GAM type models now, and even splines I think aren't always that common, even though they might be super powerful. It's kind of often easier as well to just get an XGBoost model off the ground, for example, and get really good scores in your metrics without having to do a bunch of really complicated cognitive work, like you're saying, Tom, about like what do you know about the covariates, and using a lot of domain knowledge. You can kind of not skip it, but you can do quite well, not without any, but like without so much. But yeah, there are more guesses. I will very quickly try to share my screen. I see that Zoom has had a lovely update, which means that I don't know where anything is anymore, if I ever did. But just so that people on YouTube are aware, we're going to be moving straight on to tree-based methods, which is chapter 8. And I will be doing this from my notes in Obsidian rather than a Quarto. And apologize for that, but I simply didn't have time to make nice slides and whatnot. So I'm reading basically from my notes, but I tried to add in different areas for questions and whatnot. So whenever you see this lovely question call out, it's a sign to like unmute your microphones and offer some answers. So just this is more like a show of hands. Has anybody fit tree-based models before, like decision trees, random forests, XGBoost, or any of the other boosters? Yeah, two. Okay, nice. So we've got some, and yeah, interesting, because I do think they'll tend to be like the first kind of serious models people will reach for, as in like beyond like a linear model. Like a really good default tends to be random forest. But okay, let's get into what actually are trees. Oh, and to confirm, you guys can see my screen, right? Okay, nice. Okay, so trees are a new type of model compared to what we've been looking at. I'd say they're very versatile. So you can use a tree for regression, you can use a tree for classification. The predictors, so let's actually change that. So that's the terminology. Like your input variables or your predictors, the things you're using to try to reach an answer, they can be continuous or they can be discrete. So they can be numbers or they can be categories. The decision trees that we're going to look at least in the beginning, but have a very clear interpretation or a very clear way of understanding what they're doing, which is they are trying to create areas of the predictor space. And I really hate using that term because it's so jargon laden. But they're trying to create different regions, almost like a linear discriminant analysis is, if you guys remember from that before, where they can just say like stuff in this region has this value. That's what they're trying to do. They're learning from the training data. What are the ways that, given the input values, we can like lay out some spaces? We can draw some nice shapes, normally rectangles, and we can say that if you're in this rectangle, this is the value that you have. In the decision tree case, so that's what we're like mainly focusing on today, I'd say they are like particularly interpretable, maybe even more so than a linear model. The book says that as well, but like when you actually kind of like look at what we're going to look at in a minute, you can just imagine reading it in English. Like this is exactly what you do. As the tree gets bigger or more complex, it gets increasingly harder to actually communicate what's happening. You might be going 4, 5, 6, 7 nodes deep and saying, well, if this, then that, if this, then that. But in principle, for decision trees in particular, you do have a very clear route to explaining to someone what's happening inside the model. So even if they're not, in particular case of decision trees, they're certainly not going to be like the state-of-the-art approaches. They can be preferable in like a business setting because you can show someone very clearly what the model's doing, which, yeah, depending on your client or what you're doing, can be very valuable in and of itself. And we won't get onto it this week, but next week we'll look at what are the approaches that you can, or what are the additions that you can give to a decision tree to turn it into potentially kind of state-of-the-art approach. And those are things like bagging and boosting, which have like really nice and clear explanations through graphics mainly. So we will be looking at those next week. Any questions here before I go on? Okay, so given that it's regression, like what do we know about our response variable?
I mean, it's going to be continuous.
Yeah, nice and easy one to get going, just to make sure everyone has paid some attention throughout the course in at least some point. But yeah, we're trying to predict a continuous, like a numeric variable or numeric output. The book uses the example of the hitters data set, and this is like a picture of the tree. So let's just like look at this actual picture and imagine kind of what it tells us, and then we'll talk a bit more about what, like, how do you actually form the tree, like what's actually happening at a lower level to get to this place. But we've got the top, at the top we've got like, are the years less than 4.5, which this is like our first splitting criteria. And then if they are less than 4.5, then we get 5.11. So in thousands of dollars, I think it was thousands of dollars, the log transformation of the salary. So I don't know what 5.1 of log is, but it's quite a big number. And that will just be the prediction. And if the person had not been playing for like, if the person had not been playing for shorter or fewer than 4.5 years, i.e., if they've been playing for longer than 4.5 years, go to the right. So like we split, we go down to the right, and then we have this new criteria. So we're saying like, have they made fewer than 117.5 hits? And if they have, the prediction is 6 of the log transformation of the $1,000 of the salary, and if not, 6.74. So interpreting this data, you're kind of saying like, generally, like if you've got a few years, like your salary is going to be lower. And then if you played for a lot of years, if you make more hits, like your salary is going to be higher, which is like, it's pretty kind of easy to understand. And you can kind of imagine just like literally just reading like, okay, if years is less than 4.5, predict 5.11. If years is greater than or equal to blah, 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 and so, will then do this. And in this kind of case, you could really walk a client through what's happening, and they would completely follow you. I think, by like greater tree, by like the 15th one of these, they might have forgotten what's at the top, but at each case, they should be able to walk down with you. Okay, so next couple of questions, and these I would say, okay, the first question doesn't have, I don't know the answer. This is really, it's kind of speculation. But why might the book authors have wanted to make the response variable like the more typical bell curve shape? As in, why did they log transform it?
I'll throw in a guess that if you, am I right in thinking that you choose your cut points using minimizing the RSS? And I feel like if you're using sum of squares, a normal distribution is just going to play nicer.
Yeah. So yeah, if you get something like a log normal out of the log transformation, yeah, I think that's probably like as fair an answer as any. I was wondering in my head, because you're just scaling all of the like outputs. You're not like changing the order or anything. Like, is it like computationally easier, or will it just have like, will it actually make the classifier any better? I'm not sure. Like, I'm not sure how it would impact the like accurate, or like the, if you properly untransform the predictions, like, do you actually get better proportional predictions? I think not.
Would it'll squeeze your points together on it? Does it give you less options for your cut points? Like you're sort of compressing the space in some way, so you've got less options that are going to equal the minimizer, if that makes sense.
Yeah, although I suppose you're splitting, we'll get on to splitting a bit more, so I don't want to say too much, but you're splitting like the predictor space based on the output of the RSS in the regression case. So would having fewer possible values, does that help mathematically?
Yeah, I don't know.
It's an interesting question. I expect there's more to it than what the little parenthesis they had in the book, which is just like, oh, just make it more bell curved, as if that's like definitely the right thing to do. I would say in the past, I have log transformed response variables, normally because I want the errors to look smaller. And that's like a psychological thing as you're doing it. But that's obviously not the right way to think in machine learning terms. I think because the decision tree isn't necessarily, or I don't think it's making any assumptions about the output variables. So it doesn't seem like it helps like reach an assumption or anything. It does seem like something they maybe did for convenience. That's something to research, or maybe a flag to for someone to look at and pop back into the Slack. Anybody else on that, or Tom, do you want to come back in?
I've just, the last thing thinking on this was in your optimizer, if you take a log, it might make the gradients easier to calculate, or like more numerically stable, because you're not going to have, maybe this is completely wrong. I feel like if you take the log of the, I'm going to stop talking because it's just words. Yeah, I think it'll make your optimization better.
Yeah, I wonder because I think we're not really we're not optimizing parameters. So did I even actually mention that at the top? It's like these trees are like non-parametric methods, right? So you don't necessarily need the gradients to like adjust the parameters in like a smooth and continuous way, like as you would in some other models.
But how do you choose cut points so you're not minimizing RSS?
Yeah, but you just want the value of, you want like to pick the lowest sum of squares. So like say you have your like split candidates, your like way of splitting. You just want to calculate this residual sum of squares for all of them and then go, okay, I'll take the lowest. Rather than use that information to go and do a bunch of updates to some weights.
So do you do it like grid search? You have just a set of candidate cut points.
We will talk about it more. So I don't necessarily want to anticipate. Yeah, let's wait till we get down a little bit. It's about the predictor space. It's kind of like grid search, except I think it's greedier. The idea is kind of like you check if you were to split any of the predictors in any of the possible values and then calculate the RSS. But yeah, let's okay, that's why I didn't include the bit about the parametric or non-parametric in the talk, because I rubbed it out and had it as a question. But okay, so I've just sort of given it away. Decision trees are non-parametric. But what does that mean? What does being parametric or non-parametric actually mean?
I've been very confused about this my whole career. I feel like I hear people use it. It means different things in different contexts, but I would be curious to hear the answer from someone who actually knows. But I've sometimes heard it as meaning like linear or non-linear, and sometimes it just means like minimal assumptions versus like more full-throated kind of like OLS style assumptions. But yeah, I'd be curious to hear what other people.
I do think that last point about minimal assumptions. So like, oh, Sophie, sorry, had you unmuted there? Or had someone
Yes.
unmuted in?
I was literally just gonna kind of like chime in regarding like when I don't like know, because as there's so many ways of describing it, but whenever I think of non-parametric, I think of not making assumptions between predictor and response. And my first thought is, because I haven't had time unfortunately to read the chapter, my first thought is thinking about how that applies to where the tree splits, like how it looks at the data and makes those splits based on that.
Yeah, so I'll give it a crack at risk of saying something probably not completely accurate. In a parametric model, like a linear model, you have your parameters. One of them is your intercept, right? You're like beta 0. And then your other parameters in a basic linear model is the slope. So you have 2 parameters, and that defines the whole model. So the way you reach your predictions is by learning the best values for those parameters based on the training data. And shuffled in with that is an assumption that you should be able to model the data with just a line, right? Whereas I don't know if that fully explains like what a parametric model is, but parametric models have parameters that you're trying to find the values for. And depending on the number of parameters you have, or like the say if it's polynomials, like the polynomial degree of the parameters, that like puts on some assumptions about what the data should be like. In non-parametric models, we don't have like these set of parameters in advance that we're trying to find values for. Which for now I will leave it at that, because we will talk a lot more about parameters. I think particularly like the deep learning chapter that's coming up. But Tom, if you want to.
Do we not have a parameter here in like the number of split points? Or is that not a parameter in the same way as it would be for?
Yeah, you still get tunable like parameters, or like hyperparameters. But they are kind of like knobs you can turn or whatnot to make the model then look very different or look like anything. Whereas, say, with a parametric model, you've got your parameters. I'm not going to say always, but I think like nearly always in advance. Like the linear model has 2, and a neural network might have like 18 billion, but that number of parameters is like set in advance, and you'll try to find values for all of them. And maybe in like a really complex model, you won't need most of the parameters, but you would still have values for them in your really complex model. Whereas the values you set for the tunable parameters, you can end up with a really simple model based on those parameters or a very complex model. Okay, I don't think that's a great explanation, but it's the best I've got. So moving on to like what actually happens, like how do you end up with this tiny little tree? Like before I do read this, I think there's a better one later. But yeah, the way the book kind of presents this 2 different ways. It has like this little way, and then it has like a more complex algorithm later, which we'll also look at. But essentially what you want to do is you want to start, if you're imagining at years 4.5, you start with all of the data in one single, like say, rectangle. And that rectangle, the data set up there will predict the same value for every single sample in your data. Like if it's in the regression case, you'll just take the mean of all of the input values. Of all of the input predictors, you'll take the mean of their response variables. You place them in the space, and you average the response variable, and you say that's just the prediction for everything. And like, it's probably quite clear that in most cases you should be able to do better than that if you actually like look at your data. So you take this one big rectangle, and then you try to split the data up into more rectangles. And you try to do that in a way that the model will start making better predictions. But you need some stuff, like without some extra stuff, like some extra ways for your model to act, like it's not really clear what you would do. So the goal, rather than kind of like the method, I'd say the goal is to get all of the possible values. So the combinations, if you've got like, say 10 input variables, like all of the combinations of those values that they can be, is to make enough regions that you do better in predicting, and there will be some stopping criteria. So as in, there will be some things you can do to the model that basically tell it when to stop making new regions. But your goal will be to get to the regions that do quite well, and maybe are not even optimal, say with a decision tree. But your goal is to cut your data into more regions so that it doesn't predict the same value for all of them, but it starts to predict like similar, different parts of the data get similar values, but dissimilar parts of your like data set get other values. And yeah, when we get our regions, so when however many there could be 5, there could be 10, it could be like an arbitrary amount. We take the mean of the region to supply the prediction. So that set of possible values of the predictors, that's what we really mean by feature space or predictor space. Like I said, it's a bit jargon laden, like feature space and predictor space. I think if you don't come from a certain type of background, like in maths or whatnot, like talk of space in these kind of things can feel kind of weird. But it's just like possible values for stuff. Like there's a range of possible values out there, and that's our feature space. And in the decision tree case, it will be rectangles. That's mainly like a convention or for simplicity. You could draw other shapes. I won't get into that now, but you could. Yeah, so those regions, they are rectangles. And when we get our rectangles, they've got different input values, and then all of this, to kind of say this again, probably for the 10th time, but all of the input values in a given rectangle get the same prediction. So like, you can kind of imagine if you don't have enough of these rectangles and your data is very spread out, like you're going to be putting really different data, giving it the same predictions. Like you're going to have high error. You're going to make a lot of bad predictions. But yeah, we've seen this before. This side is RSS. So we're going through all of the rectangles where the rectangles are J, and then we're just summing up the error. And what we want to do is we want to minimize that objective. Like when we make a split to create new rectangles, we want it to be the case that our RSS like comes down, or at least doesn't get worse. And there are cases where if it doesn't come down, we still might want to make the split anyway. But we'll kind of leave that for now. And yeah, we want to minimize our, in the splitting, we want to minimize the training error, right? So we want to create this tree that minimizes the training error. And that's our objective in splitting. We'll also talk about how we maybe want to like select the final tree a bit later, which might be different to how we actually create the tree. But we want to make splits that make our predictions on the training data get better. And this model up here, this one can be represent like the rectangles are here. So what kind of strikes me is like this model is quite simple, and you see like there's this person who's been batting for like 24 years, and they're going to get the same prediction as someone who's been batting for like 4.6 years. So if like there's an effect of length of career beyond 4.5 years, like if you just continually earn more money based on the number of years, then these predictions are probably going to be quite wrong. Whereas if, say, like the actual relationship between like years of experience and the response variable is that at the beginning it's low, in the middle it's high, and at the end it's back low again, like maybe the biggest error is not going to be with this one, but like with these in here. But you can kind of see with this simple model, like we're covering a lot of ground in this little rectangle. So maybe we would think that more rectangles would be better. Each rectangle here, as you're seeing it, which is like being used to generate predictions, they are terminal nodes. They're the end of the tree. So after all the splits, you get down to the like, decision nodes. And those are what we're representing as these rectangles. Just a bit more terminology is that the non-terminal nodes, so the stuff further back up the tree, they're called internal nodes. And like the splitting criteria, they are branches. That's like the proper term for them. So what do, I kind of gave away what I noticed, but what do other people notice about this tree map? Like, I'm not saying there's a right answer, but like, what kind of things do you think might happen based on like predicting on the data using just this?
Maybe not for this specific example, but I think what's interesting is that you could get like, you can capture very non-linear relationships. So say you said there, you've got a very linear, assume there's a linear relationship between years and salary or hits. It's not going to work very well. But if it was something else that was very, I don't know, after you've worked 10 years, you lose loads of money, you're going to find a split in this that's going to capture that really nicely and quickly in a way that you're going to need quite a high dimensional, high degree linear model to capture. Whereas get it in a couple of splits.
Yeah, definitely. Okay, and then so the second question, so what do we think about the number of splits and the bias variance trade-off? Like what's going to happen as we increase the number of splits? Like what will happen to bias? Tom, you're like my star pupil today, so
That's I won't answer anymore.
Seems like as you increase the number of splits, the bias will go down, but the variance will go up. You get more flexible with more splits, but you know, your model is more likely to make different decisions based on relatively small differences in the underlying data, I guess.
Yeah, no, I think that is the right answer. The way, you know, even like I think it's quite intuitive once you start getting the bias variance trade-off, right? Like, that's kind of always the answer. Like, you make your model more flexible, it's like, well, like bias goes down and like variance goes up. But if you had like a single rectangle for every single point, you know, each point just sits in its own rectangle, like and there is a caveat that provided your input data is not contradictory in parts, like you have the exact same input variables, but you have like different values for like the response variable, which is obviously perfectly possible if you're not capturing all of the variables that are relevant, and you're building a model that's like simpler than it could be. Then you would essentially get to the residual sum of squares would be 0. You would just every single in training that is. So every single training example would just be predicted its actual value. And like, I don't know, maybe that sounds good, but as soon as you get to testing, like that's not going to happen. And your predictions are going to be all over the place. You're going to capture a lot of the noise. So it's like doing a k nearest neighbors model where like nearest neighbors is 0 or whatever. Like you're just looking at me and myself and I, and like that's the prediction. And likewise, if you go the other way, if you just have one rectangle, it's like you're not capturing any of the relationship. You're just predicting the mean of the values. So you have extremely high bias there because you cannot model. You just can't model anything really. Like you're just taking a single value. So yeah, number of splits up, bias down, variance up, and vice versa. So to come back to kind of Tom's question earlier, like the splitting procedure, and I have just kind of talked about this, but you just start with your single region, and then you split that region into 2. So you make one split, and you want to come out of that split, out of all the candidate splits, you want to take the one that at that exact point will reduce the RSS the most. And I don't want to preempt some of the questions later, but you could imagine there would be other ways to choose your first split, but I won't talk about them now. The split happens on a single predictor. Like if you saw before, we're like going a year's 4.5 or lower. Our hits, blah, blah, blah. Like we're not kind of getting some amalgamation of the predictors, like getting an embedding and then splitting based on that. Like we have our candidates are our predictors, and we're going through the predictors. We're looking at all of the possible values, and we're saying, if I split at this one, what's my RSS? Like, then so go predictor 1, like value 2 is like, yeah, I split here. What's my RSS? Now go to predictor 2, like value 1, and say like, what would my RSS be? And you're just like running through all of these possible values, and you're going to have one or a number that get to the lowest RSS that you can get. I don't actually know what happens in ties, like if different values of predictors or like the same predictor but different value, or different predictor but different values come to the same lowest value. I actually don't know what happens. But yeah, you want to take like the argmax or the argmin of the RSS, so the lowest possible value. And you just keep doing this. So like you made your split on years, and then you go, okay, I split by years and I split at this value. Now I'm just going to look again. Is there a way that I can split on years that of the remaining values that gets the lowest RSS, or should I actually split on a different variable now and look at that variable, look at all of the like possible values, calculate the RSS, and just keep splitting based on the outcome of the RSS calculation. And let me just make sure I'm going to say something. Okay. There are like that we haven't actually covered yet, but in your hyperparameters or in the values that you set, there are ways to like make sure that the splitting stops at the point that you're after. It's like the depth of the trees, like the number of splits, like the maximum number of splits you can have. Once the tree reaches that depth, like stops. So no more splitting. And you could set another one. The book gives the example, like keep splitting until there is no group that has 5 or fewer observations. So as soon as you get to the point that a group has 5 or fewer observations, like stop splitting. That's like your final tree, at least until you start like playing with it, or pruning it, which we'll look at a bit later. And yeah, now you've got your observations, you split based on those like criteria. Like I had split on this predictor at this value, then I split on this predictor on this value, then I split on this predictor on this value, and then I get to like the max depth of my tree. Then you just say all of the input data can now be like placed in a rectangle. There's a rectangle for everything. Each rectangle gets its mean value calculated, and then every single sample that was in that rectangle gets the same value, the mean value. Okay, is the splitting procedure bottom up, top down, and why?
Are there technical definitions to bottom up or top down? Or is this sort of like in the colloquial sense of the,
I think
okay.
I think they maybe do describe it as this term,
okay.
or I've just maybe put a colloquialism on. But yeah, I would say there is a difference of kind of what's happening in a bottom up. Sorry, wait. I mean, yeah, bottom up or top down process. Yeah.
So I'm unsure of the technical definition, but like colloquially, it feels more bottom up insofar as it's kind of like starting with the data, so to speak. But I could think of other metaphors in which it would be top down. So
yeah, I think that's fair. Not a great question then, but the answer I had was like it's top down. So you start from like all of the data, right? And you've just got it all, and then you make the splits. So it's all grouped at the start. It's all like organized, and then you just keep splitting downwards. There would be some other procedures where you would start from like individual observations, and you would find like what's the like nearest neighbor of like this observation, and you start going upwards like that way. But this way you're coming down from all of the data. You're going from like one group, more groups, more groups, more groups. Whereas you could, and lots of algorithms in different ways, go like individual samples, put them together, and then look at the groups that you've got, and then make a decision to like join some groups, or maybe not join groups based on a criteria or criterion. Does anyone know, like, so when you're like at the start of the splitting procedure, you've got one region, and you make a decision there based on the best RSS value that you can split right there. Is anyone aware of like different types of search procedures, and what that procedure is that it's using, and what alternatives like there might be?
I don't know if this is an actual method, but you could just look further ahead and calculate a few steps in advance. You obviously you're spending computation, but hopefully at the gain of making a better decision now.
Yeah, no, exactly. So they call this like a greedy search. And then others would be like, maybe you do, yeah, like you say, you do multiple splits, and you see, well, like, okay, maybe that split wasn't optimal at the first time, but it leads to a more optimal outcome later on. So that's going to be like one of the big weaknesses of a decision tree, is that you can't look further ahead. And I think this one, like an example or say an analogy of like how this could mislead you, I'll actually go with this one. I haven't fully thought it out, but I think it kind of captures it in my mind. It's just like, if you were trying to traverse a maze, so like at any point in the maze, you can just look left or right. And if you can just peek out and you have this criterion that says like, I will just choose whichever one has like the longest, like the most distance I can see in front of it, like doesn't lead to a wall in the most distance. So like every time I split, at that exact split, I can travel as far as possible. Then you can kind of imagine quite quickly that that isn't going to lead you most likely to the best outcome, because maybe there's a really short one, or like in the actual like way to traverse the maze, there's like a long path that leads right to a dead end, but there's a short one, and then up from the short one, there's a longer one. In the decision tree, like you would have just gone to the long one, and like you wouldn't have like traversed the maze. It's not like an exact analogy, because obviously in the maze you can just kind of turn around and like go back and be like, oh look, I could have gone this way. But that's kind of what it's like doing. It's like it's really short-sighted. And in other alternatives, like if you can search 2 levels deep or 3 levels deep, you do like a type of beam search. You can get to better outcomes by spending more time, as Tom says. And that's also kind of like why splitting procedure isn't guaranteed to reduce.
I'm not at all suggesting that this is one search method at all, but I was reading a fun paper, and some ideas they posited was that this researcher was constructing a neural network as like a version of a soft decision tree. So the idea was trying to leverage how neural networks work, but making them interpretable. But I haven't read the whole paper, and I saw some critique online of it. So again, I'm not saying it's an actual search, but I just thought it was interesting considering it was a question that I saw that recently.
Yeah, nice. I think they're making a lot of waves in terms of actually making neural networks, not quite decision trees, but like getting the decisions out of them, or like trying to understand how they happen. I am a tiny bit mindful of time. This has gone a lot faster than I expected. We are like a few minutes from the end, so I will go on. This is like a denser, like a more complex tree that they actually give a bit further down through the book, and you can kind of see like it has more depth. So like there are more splits, and it's more complex. And in this way, I think maybe you can see like it's kind of top down. Yeah, maybe that is also just my my terminology.
No, that makes sense. That's intuitive to me.
It's actually really interesting about the terminology, because in psychology, when we use top down, we use it in the way like Jack uses it. But I've noticed in data science, they use it the opposite way. I've noticed they use like high level and low level to basically mean the opposite. And my brain is like, oh wait, it's not what I think it is. So it's interesting how the terminology can be changed around to mean exactly the same thing, just on the opposite side of the semantics.
I got caught out by that one once before. Someone said that I'd given a really high level explanation once, and I thought they were like commenting that it was a really good quality explanation, but they were actually saying it's like superficial.
Yeah, I had to get my head around that as well.
Yeah, I was like, oh, thank you. And they were like, no, like, what you like.
You've got a high level understanding.
Yeah, exactly. Thank you so much. That's really kind. Yeah, it was pretty funny. Okay, so on this one, a quick one, like if years less than 4.5 is depth, did I say 1? Yeah, so we're starting counting at 1. What's the maximum depth here? And it's not a trick question. I should probably get the answer there.
Is it 5 on the right? On the rightmost? Is that right? 1, 2.
I hope so,
3, 4,
yes,
5.
because that's
Yeah,
what I
okay.
got.
Yeah. Okay. Yep.
Yeah, I think so. You got like, so this is 1, 2, 3, 4, and then yeah, 5. Okay, so we are at like 6 o'clock. I think we shouldn't try to get into the pruning because it's kind of quite important, and it does actually. I'd say it's worth dwelling on. It takes a little bit, maybe longer than I expected. So next week we will continue tree pruning. We'll go back through the algorithm, and then we'll get on to, well, we didn't even get to classification. We'll get onto classification, and I will maybe try to budget for time a little bit better. I think it's one of those cases, you know, like if I had more time, I would have written you a shorter letter. But yeah, thanks to everyone for coming today. Thanks for joining in. It's really helpful that when the questions came up, it wasn't just like silence and then like me answering.
Thank you, Jack. That was really
Yeah.
interesting.
Thanks.
Thank
Great.
you. It's really interesting. It's nice to get away
Yeah.
from the algebra of models, linear models.
Yeah, I do think the trees they are, they're a bit more not even intuitive. They're just a bit more fun because they're like non-parametric and stuff. At this high level that we're talking about them, they're more interesting or more fun. Right. I've got to get to tennis club, so I actually need to dash. Oh, I'm gonna be late. Right. Thanks
Okay,
everyone.
Thanks.
So see you next week.
See you guys next week.